I welcome you all for this presentation. In this presentation, we are going to discuss about MACs, that is message authentication codes based on hash functions. So only the name HMAC. This is the overview of this presentation, that is keyed hash functions as message authentication code, then HMAC design objectives, then the structure of or block schematic of the HMAC and the working principle of HMAC, then HMAC security, followed by summary of this presentation. In the last presentation, we have discussed about the message authentication code. Now you know the difference between the hash function, then message authentication code and the encryption process. Because in the hash function, what we are doing is just we are getting a message, we are applying that message to a hash function and we are getting message of variable size and we are getting a fixed size value. Just we are applying a message to a function and we are getting a fixed size value. That is a hash function. Encryption, you know, we are applying an encryption algorithm to the message with the help of the key and we are getting the ciphertext. That is encrypted message we are getting. So, but this encryption process, we can perform decryption, the reverse of this algorithm. If you apply, we can obtain the plain text. Whatever the input we are giving, we have to apply the reverse of the algorithm, that is the decryption algorithm, and we can get the input, whatever the message we are sending. But the difference with this hash function, then encryption as well as the message authentication code is, in the message authentication code, what we are doing is, we are just applying a function to the message as well as the key and we are getting a output of some fixed size value. But the difference between the in the encryption also we are applying a message with the key. In the message authentication code also we are applying a message with the key and we are getting some value. But the difference between encryption and this message authentication code is, this message authentication code is not reversible. That is just like if we apply a decryption algorithm to the encrypted code, we can obtain the plain text. But this is not possible with this message authentication code. So this is the basic difference between hash function, then message authentication code and the encryption process. All of you must aware this. These are because in all the techniques we are just applying we are giving a message to a function and we are getting some value. What is the purpose and what is the difference? In order to provide authentication, these three things act as an authenticator also. This hash function also acts as authenticator. This encryption process also acts as authenticator and message authentication code also acts as a authenticator. But there is a difference between these three things. So we need a MAC based on the hash function. So we are having a message authentication code. Separately, we are having a hash function. In the hash function, what we are giving? We are giving a variable size message as input to the function and we are getting a fixed size value. In the message authentication code, we are giving a message, we are applying we are using a function with using the message as well as the key and we are getting a fixed size value of the message authentication code. If we combine this message authentication code with the hash function, what we will be getting? What are the advantages? Because we are merging the advantages of these two techniques. So because hash functions are generally faster and the crypto hash function code is widely available. So only we are combining this MAC based on this hash function. So we are merging these two techniques. So hash includes a key along with the message. Generally, in the keyed hash, the original proposal was keyed hash equal to hash of key and message. So keyed hash means here we are using a hash function. We are giving input to the hash function as message as well as key. And in the generally in the hash function, what we are applying? In the hash, we are only giving the message. But here we are using both the message as well as the key to the hash function. But there were some weaknesses available in this keyed hash function. So only that makes us a base or foundation for this HMAC, that is MAC based on the hash function. So let us see how this MAC is implemented. So these are some of the design objectives. These are the main design objectives of the hashed that is message authentication code based on hash function. That is, here we are using without any modifications the hash functions we are using. Then we are allowing for easy replaceability of embedded hash function. Embedded hash function in the sense in the previous presentations and all we have seen about secure hash algorithm. It is a hash algorithm. It's a very famous algorithm. Or we can use MD5. Later on we will see MD5. So these are some of the hash functions. So we can use any of the embedded hash functions in this HMAC. Then it preserves the original performance of hash function without significant degradation, and it uses and handles keys in a very simple way. Have well understood cryptographic analysis of authentication mechanism strength. Mainly this message authentication code it acts as an authenticator. So what we are using is we are just using the hash function with the message authentication code. So these are some of the design objectives, and these design objectives we are incorporating in the implementation of HMAC. So this HMAC is specified as an internet standard, that is it is given in RFC 2104. There all the implementation details are given. Those who are interested in this HMAC can go through this RFC 2104. This HMAC uses the hash function on the message. Here only one step only. The full HMAC is given in a single formula. So how it is applied is HMAC of HMAC of K of M. What is K? K is the secret key and M is the message. So here we are applying the message as well as using the message as well as the key. So HMAC of K of M equal to hash of, this is the general hash of K plus XOR OPAD. What is K plus means? K plus means it is key with some paddings added. Padding in the sense, in order to make it suitable for some B bits are used here, because we are dividing the message into different blocks. That key has to set with the, it must be of equal size with the message block. So we are just padding some bits with the key, that is called as K plus, that is XOR with OPAD. OPAD is some specified padding constants only. That is some hexadecimal number is there. In the next slide we can see that. So K plus XOR OPAD. Then we are concatenating with this hash of K plus XOR IPAD. IPAD is also another padding constant. That is also a hexadecimal number. That is padded with, that is appended with the message. So overall this HMAC is represented as a single formula only. So what we are doing is hash of K plus XOR OPAD, that is concatenated with hash of K plus XOR IPAD. Then here where is the bracket is ending? Here this is open bracket. Here it is ended here only. So hash of this hash is applied with the whole term. So first it is applied with K plus XOR OPAD. It is concatenated with again hash of K plus XOR IPAD, that is concatenated with the message. So for this whole the hash is applied, that is the HMAC. In the full authentication code hash function is applied. So here K plus is the key padded out to size, that only I already told you, and OPAD IPAD are a specified padding constants, that is some hexadecimal value. So over it is just 3 the hash calculations than the message reads alone. So here the hash function, see here hash of, that hash function you can use any of the hash function, whether it is a MD5 or SHA. In the SHA many variants are there, any variants you can use. Ripe MD 160, Whirlpool, these are some hash function, hashing algorithm. So we can apply any hash function using this. In the place of hash you can use any of the hash algorithms. So this is the block schematic of HMAC. That is, we already told that is K plus is K is a secret key. K plus is K padded with zeros on the left. That is, the message is divided into different blocks. This is Y0, Y1 up to YL minus 1 is there. This is the message. So this message is divided into blocks of size B bits. So we need to generate a B bit SI only. So the stream SI is of B bit size. So what we are doing is we are just padding this K plus with the secret key. We are padding some zeros on the left, padded with zeros on left, so that the result is B bits in length. Then iPad means iPad is 36 in hexadecimal, that is 001101110. So 36 in hexadecimal, it is repeated B by 8 times. Because here we are performing XOR operation. This is XOR operation. So if you want to perform XOR operation, both has to be of same size. So here this iPad is repeated B by 8 times. So K plus is K padded with zeros on left, so that the result is B bits in length. So in the first step, what we are doing is we are just appending some zeros with K. Then we are XORing K with iPad. So we are getting a stream SI of size B bit. In the next step, what we are doing is the result of this K plus XOR iPad is appended with the message, that is Y0, Y1 up to YL minus 1. Here YIC, ith block of message M. So message is divided into different blocks of size B bits. So it is just appended. Then the stream is applied to the hash function. So only we have seen that hash of. Then we had a K plus XOR iPad. Then we are applying this to the hash function, and here we are having a initialization vector, that is initialization value is there. So in the initial value to the hash function. So here we are doing bits, and using the hash function we are getting a n bits. So hash of SI concatenated with M. So SI concatenated with M is this one. SI concatenated with M is applied to the hash function. So the result is padded to B bits. Then what we are doing is, again we are doing K plus XOR OPAD. OPAD was 55C in hexadecimal. It is also repeated B by 8 times. So K plus XOR OPAD, it results in B bits, that is called as S0. So this S0 is concatenated with H of SI concatenated with M. So these are concatenated, and this is applied to the hash function. Here also we are having an initialization vector of n bits. So n bits, the result of this hash function is HMAC of K comma M. So we are getting as n bits of size of HMAC of fixed size, that is n bits. So this is, in one equation we have represented the full HMAC representation, but it is in this pictorial representation it is explained somewhat in a detailed step. But in the one step itself we can explain fully about the HMAC. It is very simple. First what we are doing is we are just padding 0 bits to the secret key, so that it is becoming K plus, then that is XORed with iPad, then it is generated a stream. That stream is concatenated with the message M, that is passed to the hash function. So while applying to the hash function, we need an initial value as well. So we are getting n bits. Then again we are doing K plus is XORed with OPAD, and we are getting a S0. That X0 is concatenated with H of SI concatenated M. Then that is applied to the hash function. Here also we are having an initial value. Then we are getting a HMAC of n bits. Let us see the steps, algorithm steps. Only 7 steps are there. That is, we are appending zeros to the left end of K to create a B bit string K plus. For example, if K is of length 160 bits and B equal to 512, then K will be appended with 44 0 bytes. That is 0x00. Only zeros are appended in order to make it as a B bits. Then we are performing the XOR, that is bitwise exclusive OR operation we are applying. That is K plus with iPad. XORing K plus with iPad to produce B bit block SI. Then what we are doing is we are appending M to SI, that is message M to SI. That message is splitted into different blocks of size B bits. Then we are applying hash function to the stream generated in step 3. Then we are XORing K plus with OPAD to produce the B bit block S0, append the hash result from step 4 to S0. Then we are applying the H to the stream generated in step 6, and then we are outputting the result, that is the HMAC. So here the hash function may be MD5 or SHAR, RIPE MD, Whirlpool, anything you can used for this hash function. So the hash function is used with this message authentication code. And coming to the security of this HMAC, that is here we are proving the security of HMAC that is related to that of the underlying hash algorithm, because here this hash algorithm plays a vital role. So in the hash algorithm we have seen two attacks, that is one is brute force attack, then birthday attack. So here also this HMAC is also vulnerable to these attacks. That is HMAC attacking HMAC requires either brute force attack on key used. So here we are using the key, that is K plus we are using, no. So with the key we can use any brute force attack. The attacker can give any attack based on the brute force technique. Otherwise the birthday attack is possible, but since key do need to observe a very large number of messages. So in the hash function we have seen about the birthday attack. So that attack is also possible here. But what we have to do is always we have to choose a hash function that is based on speed versus security constraints. Because why we are going in for this HMAC? In order to provide a faster thing. That is the hash function will perform faster. So only we are just combining this hash with the MAC. But always we have to keep it in mind. We have to choose a hash function in such a way that it has to compromise both speed as well as the security constraints. Then we can choose any of the hash function with this message authentication code. But this hash function is also, HMAC is also vulnerable to some attacks with respect to the key or the used hash function. So in this presentation we have discussed about the need for keyed hash function as MAC, then the HMAC design objectives, then HMAC and the security of HMAC. So in the next presentation we will be discussing about the MD5 and SHA-3, because those hash functions we are applying with this HMAC. So we are discussing that MD5 and SHA-3, those are very famous hash functions. Thank you.